Alright, hell yeah. So a commenter wanted me to do a problem, and it's this one. This is the Indian National Physics Olympiad 2008. Hell yeah. And so this is question number 2. And so what we have here is, it's a ball. And it's going to have some sort of velocity off the top of a very, very tall building. Because even in part D, we're going to give this, cliff. This is going to be a cliff of 500 meters. And that's hugely substantial. Hell yeah. And what we want to know is like how long is it going to take to reach the bottom. And so this problem has air resistance. And so what happens is that air resistance is proportional to velocity. And hell yeah. And even that like right now you might just be like hella confused. Where's the fundamentals? And so back to Newton, if we have a mass, and just pretend like this mass is floating in outer space, and it has zero velocity. If I apply some sort of force on this mass, well, we have this equation, F equals ma. This is the relationship between applying a force on a mass. We are going to have acceleration. And then definitely think of acceleration as a change in velocity, per unit of something. You know what I mean? And when we have this, the units on it will be meters per second squared. And then so don't write it like this. Write it like, or it would be meters seconds to the negative 2. And sorry if I said that wrong. Meters per second squared. So write it like this. Write it as meters per second. Because now you can easily see that this is a change in velocity per change in time. And usually when we have units, or if you do have a number that's like, hey, 10 meters per second squared, we can write it like this: 10 meters per second per 1 second. And this is going to be your change in velocity and change in time. And incrementally your change in time will be, 1 second. Now, for gravity, this doesn't change. You know what I mean? Well, and it kind of does. Every time we bring up gravity, I definitely like to write Newton's gravitational equation, where you have the force of gravity. So if I do have some sort of mass and I have the Earth underneath, the force of gravity would be the force acting on this mass. That's the force of gravity. It's going to be equal to the gravitational constant times this mass, little m. This is the mass of the Earth, big M. And then we're going to divide it by the radius of the Earth squared. And the reason why we do radius, well, the radius just gets us to here, but essentially you're going from the center of one of the masses to the center of the other mass. It doesn't matter how big or small these are, it just happens to be whether you're on top of Everest or chilling at the beach. The difference here between that height, you know what I mean, it might just be like 30,000 meters. Well, the radius of the Earth is 6 million, so we have 6 million, and then let's show where 30,000 meters is. And do I have that right? Is Everest 30,000 meters, or is it just 30,000? Holy hell! Well, I think I'm totally wrong on this, but what is Everest in meters? I don't know, but I know a plane. It's always good to get a reference. So a plane can be like what? 5 miles to 7 miles up, and there's going to be 5,000 feet. So I think a plane can go 35,000 feet. Let's just divide by 3. That's 10,000 meters. Yeah, so maybe Everest is just like 10,000 meters. So let's throw just a 10,000 in here, and you can see that if we had 3 significant figures, well, if we were on sea level or Everest, yeah, it might change this by 1 significant figure, but very little. And so that's why we have, that's why we just use the radius of the Earth. Don't forget to square it. That's this force of gravity equation. Hell yeah. But, you know what I mean? Our force of gravity is not going to change much from And so let's throw an asterisk on this radius of the Earth squared, because, yeah, if I'm dropping something from the top of Everest to sea level, well, hell yeah. My radius here is going to be the radius of the Earth plus maybe 10,000 meters. But once we get here, once we hit sea level, this mass is just the distance from the center of the Earth to the center of the mass would just be the radius of the Earth squared. If this number is bigger, your force of gravity on top of Everest is going to be smaller. It's going to accelerate slower compared to at sea level. Okay, hell yeah. So it's always good to, simplify things, but then ask yourself, why are we simplifying it? Especially if there's a linear relationship. Have a light bulb go on that's like, hey, is that always linear? Or if I change this problem around, when does that not become linear? All right, hell yeah. So now let's kind of get to the goods. So yeah, we apply a force on this mass, it's going to accelerate. You know what I mean? I'm going to get a known value for this force. I have a known value for this mass. So I know the mass, I know the force. We have an equation or relationship that involves three things. You can rearrange this equation any way you want. So you can solve for acceleration. That's just going to be force divided by mass. Those numbers we know. And so hell yeah, now we know a number for the acceleration. So if I apply this force onto that mass, I know its acceleration. And it's going to be in the direction that the force is being applied. All right, hell yeah. Okay, so what we're going to do, first let's simplify this problem. And the simplest thing to do is just drop a mass off a cliff. This is going to have zero velocity the second I let it go. We're going to have that force of gravity. And I forgot to say that this force of gravity, these three things, because they're unchanging, the mass of the Earth, the radius of the Earth, and the gravitational constant, these are just 10. And that's what we're going to be using. A lot of these tests, like, what do you call these? Like tests? Like challenges? You know what I mean? They're going to use the gravity as 10 just because it makes the numbers come out just way easier. So hell yeah. And what does that mean? So we would have the force of gravity is just the mass of that object times g. And g is going to be 10. So we just have that. These three things are what we're going to call g. Force of, what the hell do you even call that? Gravitational acceleration. Sometimes, you know what I mean, you just use it so much, you're like, oh yeah, the acceleration of gravity. Yeah, that's the accelerate, because F equals ma. This is going to be your acceleration due to gravity. Hell yeah. Alright, so we're going to do two things. One, we're going to drop this off a cliff and no air drag. And then the next one, we're going to drop this off a cliff, and now we have some sort of air drag. And so, from a force perspective, we know that if there is air drag, at some point this is going to hit like a terminal velocity, where just the velocity is constant. Alright, so keep that in mind. In the simplified approach, we know that, hey, we're going to have an acceleration that's equal to g, 10 meters per second squared. And I guess, how did we figure that out? Well, we said the force of gravity, we knew it, well, how did, oh, yeah, that's where this is crazy. This needs a separate note card. So you have this F equals ma relationship. I see a mass, I see a force, and maybe I want to know the acceleration. We have this equation that says the force of gravity is the gravitational constant, mass of the Earth, radius of the Earth squared. Cool. That's this. That is the force. So that's equal to mass times acceleration. Okay. And then so if I want to solve for acceleration, I say the acceleration is, well, the masses cancel, and I say the acceleration is gme, radius of the Earth squared. So that's where, yeah, it actually, you're losing brain cells by calling this g. You know what I mean? And then just getting on with life, because especially because you have this relationship. F equals MA, and out pops mg is equal to MA. And it seems, it almost seems nonsensical. You know what I mean? Like a tautology or something. But it just shows that the acceleration, I mean, this is always the acceleration of this mass when a force is being applied. Or said any other way, you have three things and they're in a linear relationship, or they're in a relationship due to this proportion, this equation. You can rearrange it three ways. Okay, so sweet. So for this, we know that the acceleration, you know, we can talk in acceleration. The acceleration of this is gravitational constant, mass of the Earth, radius of the Earth squared. It's going to be that value, which is just 10 meters per second squared. And this A is equal to G. And so that's where we have G right there. But, you know what I mean? You know, you still have the long road where you're just like, hey, let's do it one more time just so we're just squared away. I have a mass, and I know that there's going to be a force on it because we have the Earth underneath us. And then there's this relationship. What is this force of gravity? It's the gravitational constant, this mass of the Earth, radius of the Earth squared. That is the force. So let's just write it in here. GMME, radius of the Earth squared. Okay, what do we know when we have a force on a mass? Then we know that Newton's equation applies. We have this relationship that if there is a force on a mass, we will have some sort of acceleration in this equation, as this equation shows that relation. So what do I know? I know this value. I know all of these terms. Know it, and then I know the mass. I know it. The thing that I don't know is the acceleration. So let's solve for acceleration. And that's what we're going to do. And we're going to be acceleration is F divided by M. What was the force? That's going to be the force of gravity. That's going to be that divided by M. So the acceleration, the thing I want to know of this mass is going to be gravitational constant. Mass of the Earth, divided by the radius of the Earth squared. So we have this value right there. We got a little carried away. So this is that value. So we're just looking at the thing circled. So we have GM, big ME, radius of the Earth squared. Now we're going to divide it by mass. These masses cancel, and you will see that we just have that. So the acceleration is that gravitational constant, mass of the Earth, radius of the Earth squared. And since we've gotten this far, definitely try to memorize this. I just think the devil or something. Alright, hell yeah. Had to throw some more juice into the camera. So anyway, if you think of this like science is the devil acronym or something, I mean, gravitational constant literally is 666. We'll get to that in a second. Mass of the Earth, what the hell is that? It's times 10 to the 24, but it's 6 times 10 to the 24, another 6. Radius of the Earth, that's 6 million. You know, that's 6 times 10 to the 6. Holy Toledo. So we're squaring it. Now, what is this, though? This is going to be 6.66 times 10 to the negative 11. Now, this might be the only one that you don't remember, or, you know, you might mess up. But what do we have here? Well, you technically have, like, a 6, because even though you have these as significant scientific notations, this multiplication is just a product of two numbers. So I can do, there's the property, commutative, I think it's commutative, where it's just like, hey, you know, you can have anyone in the community mingle or whatever. I don't know. But anyway, so you have, and let's just round this to 6. So we have this 6 multiplied by this 6, and then we have this squared, so we're going to have 6, 6. Those are all going to cancel. Cool. So now we have this is 10 to the 6 squared, that's going to be 10 to the 12. Upstairs we have 10 to the 24. And we already know that this is going to be equal to 10, or like 9.8. And so this has to be 10 to the negative 11. So we're going to put 10 to the 11 downstairs. That's what the negative means. Get it downstairs. And this becomes 10 to the 23 divided by 10 to the 24. And then so you're just going to get 10. Alright, so we are done with that. I don't know why I enjoy going over that, but that is a fundamental. Like, if you don't have that, and that's just like one thing that I've always told myself. Anytime a physics problem comes up where you get this, like, weight is equal to mg, holy hell, if you do not use this relationship, I think you're just missing out. You know what I mean? Like, if you only start using this relationship when you get into, like, oh, you're like, oh, I'm going to work for NASA now. I'm going to work on stuff that's not on the Earth, you know? Well, hell yeah, then these values change. But cool. All right. So hell yeah. So we did it. We have F equals ma. We wanted to solve for acceleration. That's going to be that force of gravity divided by m. The m's are going to cancel, and we just get 10. So the acceleration is 10, and I think it's a bummer that you're going to say g is 10. You know what I mean? Because yeah, like where does g go into the equation? You know what I mean? Are you going to say the force of gravity is mg? You know what I mean? Like F equals ma, but instead of a, you're going to call this g? Not really. Like, that's not true. You're still, see, that's not true. You're going to say F equals ma. I have a mass. I'm applying a force, the force of gravity, and I want to know the acceleration. So we have this. We have g m me, radius of the Earth squared. All of this is just one big constant. So over here I have mg is equal to ma. So therefore the acceleration of this mass is g. So the acceleration of the mass that has a force is g. All right, hell, and I swear, even that's a head scratcher. Cool. All right, so we have the force of gravity is making this accelerate, and this equation is due to the relationship that Newton came up with. It's this. This is what Newton came up with. Force of gravity. He you know, this is a observation. Cool. And we're going to say that this is constant, even though it's not constant. It's a function of the distance. And if this is going to, even if it has zero velocity, acceleration means it's going to change in velocity. Even after 1 second, it's going to have a velocity. And it's going to have an average velocity. And it's going to cover some distance. So we're getting closer. So this radius of the Earth term is getting smaller. And that means that this force of gravity is getting bigger. But we just pointed out that the difference between Everest to sea level really does not change this value hardly at all. So we're going to say this is constant. But hell yeah. I mean, but if you don't go over that, then when we come to like air resistance, I don't know. I just think, I don't know. So we can totally move on. So we have the simplified version done. Alright, hell yeah. Now there's two different ways to do physics. One is by observation, you know what I mean? By like observing something. And that's all F equals ma is. You know, when you have a mass, and then you're saying, hey, I know that I'm applying a force of this magnitude. And I'm going to call, like, whatever this interaction is, a force of that magnitude. I'm going to quantify it as such. And when I do so, and apply that, you know, quantity of whatever that is, whatever a force is, then I'm going to see something. I'm going to see a change in velocity, which I can measure by, you know, seeing this mass at rest. And then 1 second later, well, one is either just seeing it a different distance away, so now it's like over here, or I could, I don't know, you know, I mean, with sophisticated equipment, I could figure out what its velocity is, you know, at this point. But that still requires, like, hey, you know, like I'm observing this mass right here, and then a small fraction of a second later I'm observing it right there. I'm going to know that distance, and I'm going to know that time it took. You know what I mean? So the definition of velocity is just change in position, change in time. And so it's very analogous to the idea that acceleration is just change in velocity, change in time. When you write it like this has to be an average velocity. It has to be the average velocity between 2 points. You know what I mean? If I take these 2 points and they're very close together, hey, that's probably a pretty accurate, you know, it's probably a pretty accurate assessment of the velocity at that point. Where if I see that the velocity is 0 here, and then 1 second later it's 10, you know, then I don't know. I'm not 100% sure it is, you know, I'd be more confident if it was like 9.99 at this point, and then at this point it was 10, and I knew the time, let's say it was just 0.005 seconds, and then I went that distance. Well, hell yeah. Then I maybe know the velocity more accurately. The velocity is this change in position of 0.01, and then the time is going to be 0.005. Cool. And this is, I'm just going to round this to 0.01. Oh, it looks like our velocity is 1, but divided by a smaller, our velocity is 2. So maybe our velocity is 2 meters per second using what we just did right there. All right, hell yeah. So when we get into air resistance, one of the fundamentals of air resistance is that it causes a force. So you have a force, they'll call it a force of drag. But just keep in mind Newton's equation, F equals ma. If you're going to, you know, if this just was in free fall, it would be increasing every second. The velocity would increase by 10. At 0 seconds, we got 0. But after 1 second, it's 10 meters per second. 20, 30, 40, 50, 60. After 6 seconds, it's going 60 meters per second. All right, hell yeah. But at a certain point, and probably right around here, you will reach terminal velocity as a skydiver. So does that just happen instantaneously? Once you get up to 6 seconds, now you're just going 60, 60, 60? No. And then what this problem is going to say is that the force of drag, and they don't even call it, they don't even use that, they just say it has air resistance, and they're saying the air resistance causes a change in motion. So this statement says the motion in, let's say, the y direction, this is x and y. This tripped me out. The fact that you would have this where it says the motion in the x parentheses y parentheses. I thought that was I thought that was x as a function of y. That is, for friggin' sakes, man. Like some of these tests, you have to figure out what the hell. Like that's not a mathematical symbol. They're just saying, and maybe it is some sort of mathematical jargon where if you have, I don't know, but all they're saying is the motion in the x and the motion in the y direction has air resistance given by these two equations. So they're just, it's a way to say respectively. Like you have x and y, and respectively, these are the equations associated with those. All right, hell yeah. So they're not, what they talk about is not the force. What they talk about is the motion of, I'll just call it D for air resistance, drag. Cool, and it's because we have this relationship. And I think this is the hardest part, is that if you, and it is a tautology, you know what I mean? Like one is explained by the other, and the other is explained by, you know what I mean, by the one or whatever. Where Yeah, so what we should see is a change in velocity of 10 meters per second every second. But at some point, we see zero change in velocity. Zero change in velocity per change in time. Our acceleration goes to zero. All right, hell yeah. But you know, when our acceleration goes to zero and this thing's still free falling, does the force of gravity go away? No, that force is still going. So what happens is that you have a equal and opposite, so you do have a drag force of drag. So it's very useful to show the forces. This problem, and I'll just kind of show you the units. They say that the motion due to air resistance is given by this equation. So let's just talk about the y. It's going to be some sort of constant, proportionality constant. So, and this constant has the units of, or it's 0.05 inverse seconds. So it's the units on it are divided by 1 second. You know what I mean? However you want to look at that. That's going to be c, and then we're going to multiply it by the velocity. And the velocity is going to be some number in meters per, you know, and you could say meters per second. Velocity is a change in distance, change in time. That's going to be a change in meters per every 1 second. So sweet. The units on this are going to be, you know what I mean? It's going to be 0.05, whatever this velocity is. And then the units are going to be meters per second squared. Cool, that's going to be meters per second, change in velocity, change in time. So this is going to be the acceleration. So the motion due to this equation, this is the acceleration due to air resistance. Cool. So let's talk about that, because if I have a force of drag due to air resistance that's building, and we're going to say that the force of drag is equal to but in this they're just giving the acceleration. So you have the force of drag is the mass times the acceleration of drag. If I knew this force of drag, if I could quantify that force, then, and I know my mass, then I would solve for acceleration of drag as just that force of drag divided by the mass. All right, hell yeah. So this problem is they're just giving you that. They're just saying, hey, this quantity is, you know, this equation, and we're saying the acceleration due to drag is the velocity in the y direction times a constant. And that's going to be 0.05 times the velocity in that direction. So that's going to be the acceleration due to drag in that direction. And when this thing flies off this cliff in this direction, we're going to have an acceleration due to drag in that x direction. It's going to be proportional to the velocity in the x direction. So those are accelerations. All right, hell yeah. So this is part one. This is kind of the introduction. And where I struck out I have not solved this yet. Where I struck out was going through the integrations, because it says obtain expressions for the position as a function of time in the x and the y directions. The x direction is fairly straightforward. The y direction, I have a fundamental misunderstanding of the integration, because I tried it like 3 different times and I was just getting an answer that was off. So this is the introduction, and then the next part will be what I want to solve for is drop this off a 500-meter cliff and then obtain the time which the ball hits the ground. That's a straightforward, and it's straightforward because the acceleration of gravity is 10, which means that every second this thing is going to go, like at 0 seconds we have 0 velocity. So if you're mapping time and velocity, 1 second, we have 10, 2 seconds, we have 20. Now, velocity isn't position, but what we can figure out is that, hey, if I'm going linearly, then, I mean, I know at 0.5, I can just see it. 0.5 has to be 5. You know what I mean? So I have a very linear relationship, and then I just find the average velocity. For this one, and let's just do 2 seconds. So the average velocity would be 10, and I did that for 2 seconds. So I went 10 meters per second for 2 seconds. Always use the units are the equation. We have meters per second, and we have seconds. What do we do to these to get what we want? We want distance. And so, hell, you're just going to multiply them. Units cancel. And so multiply these, you get 20 meters. All right, so after 2 seconds of pure free fall, I can go 20 meters. What we're going to find is after 10 seconds, if I boosted this to 10, velocity is going to be 100 meters per second. Average velocity would be half, 50 meters per second. We did that for 10 seconds. And hell yeah, we got 500 meters. So there you go. So that's just kind of like the quick and easy to be like, hey, if I just drop this off a cliff and there's no air resistance, it's going to take 10 seconds. And so that's the intuition that you should have, like just knowing, because the acceleration of gravity is a constant, it's going to be fairly straightforward. But now in the second part of this, what we're going to do is we're going to figure out what this air resistance does on the acceleration. You know what I mean? And hell yeah, so let's do that. All right, and we'll just walk our way through like what it says. It says that the acceleration due to this air resistance is proportional to the velocity. So even that could be a handful. But let's start at time is 0. So we're just going to say at time is 0, our velocity in the y direction. And we're just going to drop this mass off this cliff. We're going to give it no velocity. We're just going to drop it. That's all we're going to do, but there is air resistance. And I'm going to jump in here because from an F equals ma perspective, the only way to generate a force is to have mass change velocity. And so the force of drag isn't just some magical phenomenon that this mass is changing velocity. No, some other mass has to change, and I guess it would be an equal and opposite. Like, so is that a law of conservation of momentum? Where what happens is when this hits air molecules, let's say this air molecule had to move out of the way. It had to go from 0 velocity to a change in velocity just to move out of the way. It has a very small amount of mass, but we have F equals ma on that. And we see that, let's say it changed its velocity from here to there, and that took 1 second. Okay, so from this, so we could figure out the force, and then we'll call it force of drag, the force that was required to move that air molecule from there to there. So here's the air molecule. Here's the force of drag that we can calculate. And the acceleration. This is why you always want to think of acceleration as a change in velocity, change in time. And so we quantified it. You know what I mean? We figured out that it changed this much velocity in 1 second, so we know that value. I know the mass of the air molecule, and therefore now I know the force. The force of drag of that air molecule is the mass times that change in velocity, because maybe we could, you have a little beacon on every little molecule of air, and it's, you can digitally figure out that change in velocity. Booyah! But that has to be what's happening. You can't just have this thing, having some sort of force without. I guess there's a few ways to get forces, but force typically is, well, now I'm going to say some dumb stuff. But anyway, so it's just a good visual of what's happening when you do have air drag. When a chunk of mass is going through air, it's the fact that the air molecules had to move. And let's say they had to vibrate. You know what I mean? Let's say this is the air molecule and it just had to vibrate. Well, hell yeah, that took a force to have that change in velocity. It was stationary and now it's like vibrating or whatever. Well, it took a force to do that. And oh yeah, now I see that, because if I have this big chunk of mass, you know, hauling down this cliffside, what was I gonna say? Oh yeah, so it does have, let's say it does have a velocity, and it hits this little chunk of air molecule. Well, what's going to happen is that this mass is going to slow down. So think of it like this. When your plane tags a bird, your plane just slowed. You see your plane's going velocity hella. Well, when it hits a bird, it's going to go velocity hella minus, you know, a small velocity because it just throttled a bird. You know what I mean? And so, yeah, so that is the conservation of momentum. Where it's just like, yeah, there's no free lunch, but it's still like that's the definition of a force too. Like you could have had this plane, and then say, hey, in the time that it took the bird to go from head to tail, you know, that change in time, because that's going to be the constant force that was applied. So you have a force for a very small short of time. So F equals ma. Here's the mass of the plane, and you're applying that force, and so you have force, mass, change in velocity, change in time. So you're applying this force, that change in time, on the plane's mass. You can figure out its change in velocity. Alright, hell yeah. And this is very observable and quantifiable of a bird hitting a plane. Now, if you just have like a chunk of mass sliding over a friction surface, you're like, well, what? You know, let's say it has some incoming velocity and then hits a rough surface and then starts slowing down. You're just like, well, how? What? You know, like, hey, Newton says this mass wants to keep going. And the only way for it to not keep going is for, I guess, something else to, you know, some other mass to change its velocity in some sort of time, change in time. And that's what happens when this mass goes over this rough surface. Just think of this rough. You ever see those door stoppers? You know what I mean? Where you tag it and then it, you know, it goes back and forth. Well, hell yeah, that's exactly what you're doing on a rough surface. This door stopper has some sort of mass. It was stationary, and now you just put it into motion. You know, so that by the time you got it to here, you know what I mean? You went from zero velocity to some sort of velocity in, let's say, 1 second. You know what I mean? There you go. So you have that change in velocity per that 1 second. So you have that value. You know the mass of this little door stopper. Hell yeah. And so it took a force to move that door stopper. So all friction, all rough surfaces is just microscopic door stoppers that you're just tagging and changing and moving mass from a stationary 0 to some sort of change in velocity. Hell yeah. And it just happens when you do that, it's a very linear relationship, so it makes problems pretty straightforward, which yeah, and ours is linear. Now this is going to be, this is true to the physics. The air resistance is going to be the acceleration or the force of drag is going to be proportional to the velocity, just linearly proportional, until you get up to faster speeds. Faster than about terminal speed, or about terminal speed, 60 meters per second. So from 0 to 60 meters per second, hell yeah, it's proportional. But after this, you get into, it's going to be not proportional, it's going to be the constant squared. It's going to be proportional to the velocity squared. However, is it the velocity? Yeah. Yeah, but yeah, it's some sort of squared. I forget what the hell squared. You know what I mean? I would imagine it's the velocity squared. Because what we have is the acceleration is some sort of constant times the velocity. That velocity is some sort of value, multiply it by a constant, that's going to be my change, you know, how fast I'm slowing down due to that resistance. So if I squared the velocity... Alright, I'm starting to like stuff like this, where you're just like, oh, I don't know something, but we can figure it out on the fly. Because obviously if it's going to be proportional to the velocity squared at high speeds, air resistance. Because if I just squared the constant, well, that's just a constant. A constant squared is just a constant. You know what I mean? So, hell yeah. Alright, so now we can take a look at our problem. And we're going to give us some values on this. You know what I mean? So this constant is going to be 0.05. The acceleration due to that drag is going to be the constant times the velocity, let's say in the y direction. So that acceleration of drag in the y direction is 0.05 times that velocity in the y direction. Okay. So we do have F equals ma, and what we're going to find is going to be the sum of the forces times the sum of the masses and accelerations. And so, and it's just kind of interesting. Yeah, I'm glad I went over the conservation, because what we're going to find is the force of drag is going to be the mass of an air molecule, sorry about this, the force on an air molecule is going to be the mass of that air molecule and its acceleration. I'm just going to write it as change in velocity of that air molecule in some sort of change in time. And so and the air in the molecules that we're moving are going to be and let's say this is where you need to have your change in time go to, you have a limit where your limit as change in t goes to 0. But let's just, I like to think of things in 1 second increments, just because even if they are off, you know what I mean, where you do need to take the limit as that change in time goes very, very small. But think about this, that every second, this chunk of mass is just going to blast its way through this column of air. So that's going to be 1 second. In 1 second, it's going to blast its way through that column of air. That's going to be the mass of the air. Hell yeah. All these molecules have to get out of the way, you know what I mean? So half go that way, half go the other way, and we can calculate the change in velocity of each of those air molecules. Cool. So we did that. Every one air molecule moves the same, has the same change in velocity. It's as if that mass of air just moving from here to, let's say, over here, you know, not, and then final, or whatever, you know, we can find the change in velocity of that mass of air. And let's say that took 1 second. Okay, so now F equals ma applies. F equals ma. We have the mass of the air. We have the change in velocity, change in time. We know the acceleration. And we know the mass. So it must have took a force. It must have took a force to do that. And the force that was doing that, I like to think of it as a driving force, was the fact that this mass, we already have some mass and velocity. You know what I mean? So this, you can think of this as like energy can't be created nor destroyed. And the whole universe is just playing out as mass with velocity. And then, you know what I mean, you're just changing that around. The Big Bang provided a whole lot of mass with a hell of a lot of velocity. And now we just, you know what I mean, we're just rearranging that. Conservation of momentum. Cool. And for a lot of classical problems, like if I want to provide a force, well, I must have to have some sort of mass, you know, that's able, you know, some sort of mass with an acceleration. I'll have to think about that, you know, more, because it's just kind of, it's like, what came first, the chicken or the egg? You know, the fact that if you can say, hey, this is a force, and it's acting on a mass, it's going to cause an acceleration. But here, this mass is going to slow, as it barrels its way through this column of air, it has some sort of velocity, and then the velocity, and let's say this is just horizontal, so this would be the x direction. So you have, it's going to blast through this column of air, the air is going to move, and now the mass is right here. We're going to say it has a velocity right here. Its velocity is going to be this minus something. You know what I mean? So we're going to have a change in velocity, a negative change in velocity. And that's the conservation of momentum. Is that this mass having a velocity is a driving force, or can be a driving force, because it can hit other molecules of mass and make them move, make them go from stationary to a change in velocity, but only by giving up some of its velocity in an equal proportion. If it hits something very tiny and makes it move, like the airplane hitting a bird, the airplane ain't going to slow down much, but from a classical physics perspective, it is going to slow down, and quantitatively and extremely accurately in proportion to F equals ma. You know what I mean? So that's kind of cool. Alright, so hell yeah. And if we have that force, so we went through that whole process of F equals ma on the air molecules, there must have been a force on the air molecules to make them change their velocity in 1 second, that acceleration. And that force was provided by this mass incoming with hella speed. The force that this mass applied to those air molecules, that's going to be the force on the air molecules, is equal to the force from the air molecules to the mass. So this is the force of the mass to the air molecules. Now, that's the conservation of momentum. That force from the mass to the air is the same as the air applying a drag force on the mass. And now I think we're there. You know what I mean? So that's in words. I'm satisfied with that. Cool. All right. So cool. We have this drag. So what's going to happen? And we're just going to go back to this. So dropping it off a cliff with air resistance now. Our velocity at time 0 is 0. Let's get a fresh sheet. So hell yeah. And, you know, just for a picture, dropping a mass off, velocity is 0. So we have time 0, 1, 2, 3. Our velocity at time 0 is 0. Okay, hell yeah. So we have the force of gravity. We know that that's going to cause a acceleration of gravity of 10. Then we have the force of drag. We know that's going to cause an acceleration due to drag. That's going to be 0.05 times the velocity. Hell yeah. And both those come from F equals ma. Alright, none of my cameras have juice. Okay, so yeah, but both these come from F equals ma, and it's the sum of the forces equals, the mass don't change. The mass is, so we can say the sum of, and the sum of the accelerations. Another way that you could write this is sum of the forces is equal to sum of the masses and accelerations, where you have the sum of the forces, force I, is equal to summation MIAI, where I forget the summation. I need to get that better, but you have N is 0 to I. I don't know. Sum them all up. Cool. But mass isn't changing. But this shows you that you can be like, okay, I have a negative, so I have a negative force of gravity, a positive force of drag, same mass, and that's going to be an acceleration of gravity. And do I put a negative on that? And then we have plus 0.05, and that's going to be the air resistance in the positive direction. It's changing its velocity. We're saying that this is positive, and then this is going to be the negative direction, positive y. Okay, hell yeah. Yeah, this might not be true, but I think it was pretty close. Cool. So, but basically, the fact that the motion, the acceleration, is proportional to the the velocity, linearly proportional. We can just go through here. So we have, but when the velocity is 0, this drag is 0. Cool. But the force of gravity is still 10. That never goes away. Okay, so my velocity is going to change. So after 1 second, my velocity is going to be 10. And then, cool, now my velocity is 10. So we do have an acceleration in the positive direction. This is negative 10, sorry about that. So we have 0.05 times 10. That's 0.5. That's my acceleration in the positive direction. We have negative 10 in the negative direction. We have a net negative 9.5 for our acceleration, which is change in velocity, change in time. But I can say this is this is negative 9.5 meters per second, a change in velocity of negative 9.5 meters per second every change in time 1 second. So cool. So in 1 second, I'm going to increase my velocity in the negative direction. So I'm having a positive value on these, but I'm just saying this is the speed. This is negative speed. Sorry about just not wanting to put a negative here. But hell yeah. So now my speed is going to be 19.5. Cool. Now my speed is 19.5. We got 19.5 times 0.05. That's going to be the acceleration due to gravity. So we have 19.5 times 0.05. That's going to be 0.975. So this is going to be the acceleration due to drag. We have gravity as 10, so we have 10 minus that. And now our change in velocity is only going to be 9.024. So we're going to go 19.5 plus 0.025. Hell yeah. And let's compare it to no drag. So we just did 3 seconds. No drag, my velocity is going to be 10, 0, 10. So time of 1, 2, 3. Velocity is, time of 0, 1, 2, 3. My velocity with no drag. 0 velocity when we start to drop it. Due to gravity, we're increased by 10. This is meters per second, time in seconds. And after 2 seconds, 20 meters per second. After 3 seconds, 30 meters per second. So we see some deviation. There's no change. There's 0.5 and change. So right here is 0.5 and change. The difference between this what it would be. Like right here, gravity is going to be 10. So this should be 29.5 minus 28.525. So this is going to be a 0.975. So here there's no change compared to no air resistance. For after the second second, there's 0.5. The velocity is the difference of 0.5 in that second. Between the next seconds, the velocity is going to be a difference of 0.975. Okay, so hell yeah. So there you go. So, and what you can do is, if you want it, because what we're going to do in the next video is like, hey, let's try to get more accurate. Because I could say acceleration is 10 meters per second per 1 second. Well, how about I do this? How about it's 1 meter per second per 0.1 second? And then I can have time as 0, 0.1, 0.2. And see, we're getting hella more accurate. Velocity is going to be 0. And then after 0.1 second, my velocity is 1. My velocity is 2. With drag, with air drag, my velocity is 0. After there's going to be, 0 times 0.05, that constant is, so let's do the acceleration of gravity is going to be 1 meter per second per 0.1 seconds. The acceleration due to drag is going to be 0.05 times the velocity. That has units of meters per second per second. I need to divide this by 0.1 to get meters per second per 0.1 seconds. So now this will be my equation, and we got 0.05 divided by 0.1. Is that right? 0.05 divided by 0.1. No, that's not right. The acceleration of drag has to equal this constant times velocity, which is 0.05 times that velocity. And so we need 0.005 divided by 0.1 seconds. 0.005 divided by 0.1. Same thing here. Acceleration is either 10 meters per second in 1 second. That's going to be a change in velocity of 10 meters per second in 1 second. Or that can be thought of as a change in velocity of just 1 meter per second, but in a very smaller time frame. It could be thought of as 0.1 meter per second in 100th of a second. Where this acceleration due to drag in 0.1 seconds is going to be just 1/10 of the acceleration that you'd expect. Cool. And, hell yeah. So, 0 velocity due to drag at time 0, so we're not going to have any change, any deviation, so our speed is going to be 1 meter per second. If our speed is 1, we're going to have 0.005 times 1 divided by 0.1. So we're going to have an acceleration in the positive direction of 0.05. Due to gravity, we're going to have a -1. So we have a -1 plus 0.05. So our acceleration is -0.95. So we're speeding up in this negative direction. That's going to be our change in velocity. In 1/10 of a second. This is change in velocity per 1/10 of a second. So now we're going to go from 1 to 1.95. And you can see that it's going to be very equivalent. After 3 seconds, 0.3 seconds, this value without air resistance is going to be 3 meters per second. This value is going to be 1.95 times 0.005 divided by 0.1. Did I do that right? Oh, not really. this part is going to be, this is my velocity, 1.95 times the acceleration is this. It's going to be 0.005, times that velocity. This is going to give me a value of 0.00975, but that's happening in a tenth of a second. And so in this tenth of a second, we're going to have a positive acceleration. Negative acceleration will be negative 1. And so we're going to have we'll see if this works. I feel like I might have made a mistake. But we have 1 minus that answer. So now we're going to have our change in velocity is just going to be 1.95 plus that, 2.94025. Now I definitely have to double check what's going on. All right, what I'm observing is the fact that we change this change in time, make it smaller. We're getting a more accurate answer. So this value is going to be 1 meter per second after a tenth of a second, due to an acceleration of gravity of 10 meters per second, no air resistance. Once we get this 1, we're going to multiply it by 0.005, and then we're going to have, so this number might have been wrong, but we'll see. We're going to have the acceleration of gravity as 1 minus that, and we get 0.995. So we're going to go from 1 to plus that. So this value is wrong. 1.995. So we just have air resistance is just causing a very, very small change. Once we get this number, we're going to multiply it by 0.005. And then we're going to do 1 minus that. Now this is going to be the change. So we're going to have change in velocity. So we're going to have 1.995 plus this change. And now we're going to get 2.985025. And so we are slowing down just a bit, but because we're not picking up much velocity, our deviation from no air resistance is smaller. But hell yeah! So now we can do this, and we can run this in Excel to get a fairly, almost 100% accurate, just by using this equation. Just the fact that this change in velocity per unit of time is going to be this equation, where c is 0.05 inverse seconds times velocity, which is meters per second, some sort of number. And this is this is acceleration in units of meters per second per 1 second. And we just showed how you can change your time frame. I could do a change in time of 1,000th of a second, and then just keep getting a more accurate answer. So sweet. So for the second video, what we're going to do is we're just going to take an increment of 1 second, and we're going to see that for this 500 meter cliff, it's going to take 10 seconds to drop and fall. With air resistance, what is your guess? Do you think it's going to be 12 seconds? Do you think it's going to be 11 seconds? Do you think it's going to be 10.5, 10.3, 10.7? I don't know. Like maybe I'm thinking more like that. Maybe, possibly. I don't know. So there you go. So so this was part 1, kind of going through just the general gist. But the calculus gets pretty tricky, where I wasn't able to figure it out. I was doing, and that's the crazy thing, because let's say you have this. Let's say we have integration of x squared, and you think the integration of x squared dx is just x to the third. Like, that's what you thought. It's x to the third plus a constant. You forgot to divide by a third. So, and you know what I mean? Like, there's, what happens with, mathematics is that you lose touch of a fundamental understanding of what's going on with that. So like even in anything like this, could we just show that if we have x squared, which is 0, 1, and then if we go 2, we're going to go up 4. And we have some sort of equation. The integration, by definition, is a summation of this value. And with a small change in x at that value of x. And it's that value, this is the height of the equation. This is y is equal to x squared. Y is the height of that equation. The height of this equation is the y value in x squared. So it could be either the y value or it could be x squared. So hell yeah. So we have height is equal to x squared. The width of this little segment is dx. And hence we have x squared dx. That's going to be, this is the volume or the area of that little slice. Now to get all the slices from, let's say, 0 to, what do we want? It doesn't really matter, but we could go 0 to 1. If I wanted all those slices, well, I would have to sum all those slices. And so that's where you get the summation, and you get, I don't know, you get an integral. And so that integral is going to be 1/3 x cubed. And hell yeah, so let's just visually see if that is going to make sense. Because what's the area of this triangle is just 0.5. This is 1 and this is 1. So I'm just going to guess that the area is 0.4 or maybe 0.37. And so when we do this integral and evaluate it from 0 to 1, what we're doing is we're finding the area. We're using, and that's where it's just like, is this a trick? You know, is the, what do you even call that? The power rule of integration? Like, at what point does it just become a trick, or at what point can you actually show, and I don't even think I could. I can just visually see and do a check on reality if this is going to make sense. But we have 1/3, 1 cubed. So hell yeah. So the area is 0.33. And I was going to say it's either 0.4 or 0.37. So we're close enough. And if we type in x squared, graph it, and then find the area from 0 to 1. This is going to be the integration from 0 to 1. And we get an area of 1/3. Cool. So we just did a double check on reality when it comes to integration, which is useful. Alright, sweet. So, and what I'm gonna leave you with is this, is that the integration and the tricks required to do integration from whatever you call it. I mean, using symbols to make an equation where if you pop in the numbers, you're going to get the answers, I don't know, that you're looking for. There's so many places for mistakes to be made. And there's even integrations where you can't do them anyway. Where from this numerical perspective, this is called numerical methods, where you're just like, hey, the accelerations are very simple. We have an acceleration of 10, and then we have an acceleration of a constant, or 0.05 times a velocity. You know, so if our time increment is 0 to a thousandth of a second, 0.002, then I know, you know what I mean, I don't have a second. My acceleration is 10. It's a change in velocity of 10 meters per second if I had a second. If I only have a thousandth of a second, well, we're going to have 10 divided by 1,000. And now my change in velocity is just 1/100th of a meter per second. I'm going from 0 to 0.01 meters per second. Cool. And then my air resistance. All right, hell yeah. And then my air resistance after, you know, once I pick up some velocity, well, now I'm going to pick up some air resistance. And I could figure out that acceleration. And, you know, I would know that it's a value per second. I don't have an increment of a second. I have an increment of 1,000th of a second. So that's the only thing to be paying attention about is like, and it's kind of cool to when you're using kind of guessing skills, is just be like, hey, I'm just going to take 1 second in increments because this value is going to be the value in 1 second. It's going to be the change in velocity in 1 second. Alright, so we're done with this. So my next video is just to get an answer for this. And I'm going to use increments of 1 second. And then I'm going to put it into Excel. And then get a more accurate answer. And then from that accurate answer, then I can go look up how to do the integrations of problems like this. Because, I mean, what you're going to have is, you're going to have acceleration is this -10 plus the air resistance, which is a constant, times the velocity. Acceleration is dv dt, -10 plus c, this is v. And then what I thought was you just, you know, let's get this. dv is -10 plus cv, and then get the dt up there, separate variables and integrate. Now you're going to have time as a function of velocity. When you do this, you're going to have, this is just natural log of -10 plus cv. I'm sure I just made a mistake right there, so that's where I'm making mistakes on this process that I don't know how to remedy. And then I'm trying to get an equation. Like obviously this is time as a function of velocity. I want to, you know, take this e to both sides and get this separated. And so I'm going to get velocity as a function of time. I thought it was just e to the negative, you know, t constant whatever. And but I could never get that equation to work out. So my math was just a little bit off. But, you know what I mean? Forget math. Because cool that these symbols can generate on a calculator. Because when I thought I was doing it right, you know, the equation that I was getting did not pop out at me that is like horribly wrong. Where I was getting an equation where my velocity was hardly increasing at all. My velocity is going to go from 0 to 10 to 20. And we just showed that the air resistance is going to be 0, 9.95. I don't know. 9.9, I don't know. And then, or it's going to be 0 to 10, no change. And then you're going to get 19.5. Yeah, that's what we had. And then 30. And this is going to be 28.95 or whatever. And then so, if my equation, due to air resistance, doesn't look like that, when I plug in, if I have an equation where if I throw in a value of time is equal to 3, if I don't pop out a velocity that's equal to 28.9, then I know that I've done something wrong. And so that's what we're going to do with the second part, is just get a value, get values for this from time of 0 to 10 or 11, so we can figure out you know, what the time is when it's going to hit and what the velocities are at each time due to air resistance in this y direction. So we're done with this. Thanks for joining me, and we'll do that second video. Booyah!